Thanks. Thanks very much for the introduction. So I'm Stephen. I work for a company called Quby. We make the Tone smart thermostat and energy display. Before getting into all that, I thought it'd be useful to give you a little bit about my background, my context. So I'm originally from the UK. I studied Oxford University, did a master's and a PhD in applied mathematics, focusing on mathematical modeling of biological problems. And a large part of my thesis was about modeling cabbage plants. So that's, come and speak to me afterwards if you want to know more about that part of my life. I actually, when I finished there, I came over actually to Utrecht for 1 year, back in 2010, working in on bird flu modeling. That was at the veterinary medicine faculty here at the campus. Then after that period of time, I started in the energy world. So originally at a startup company in London, where we were focusing on what's called demand-side management. So that's controlling electrical devices to turn them on and off in response to indications of supply versus demand on the grid. So a lot of algorithm development, modeling, and making all of that work at scale. Following on from there, in 2014 I came back again to the Netherlands, working at TNO. There I was really concentrating on taking the concepts from the company I was working in London and seeing how that could be broadened out onto the European and Dutch level. So working with a number of European grants to see what the possibilities were there. Since 2016 I've been working at Quby, and now my role there is the head of data science. So Quby, we're the company behind the Tone smart thermostat. I'll tell you a lot more about that in a while. We're a company based in Amsterdam. We're around about 110, 120 people. Very international. I think we've got about 28, 29 different nationalities across the staff there. I lead a team of data scientists. We currently have a team of 6 data scientists, work very closely with data engineers. And that forms part of the larger groups working on various different implementations and products across the company. Give you a little bit of an idea of our history. We started back in 2004, when the company was originally founded as Home Automation Europe. So this was way before the iPhone was invented. So no one had even used the term Internet of Things. That was still really fresh and new. We were formed by 3 co-founders. They really wanted to control items in their home. So for example, being able to automate the opening of the blinds within the living room. Over time, various different prototypes were formed. You can see one here in the middle. It's a nice a device I'm sure you'd be very happy to have in your home. It's perfectly safe. And over time, started more developing towards energy insight and energy displays. So just before 2012, we formed a partnership with NACO. And NACO were typically, so they're a large energy company in the Netherlands, sell both electricity and gas to around about 2 million customers. So the energy market is changing quite a lot now. So they were wanting to make sure that they were able to offer a great service to their customers and make sure that their customers would stay their customers, rather than getting to the end of the year and looking to see which other energy company they wanted to move to. So at that time we came up with the concept of combining an energy insights display with a smart thermostat. The idea behind that is everyone needs a thermostat in their home to control the heating. You can offer some great functionality by being able to control your heating remotely using a mobile app. And that is also a way of getting people engaged with energy insights. So combining the 2 products together led to the creation of this. This is the first version of our Tone smart thermostat, launched in 2012 with NACO. Over time we've actually rebranded to Quby, a more generic name. We've launched this year an updated version of the hardware. And we're now starting to move into different sectors as well. We launched with Interpolis, who are a large insurer within the Netherlands. We launched a service expanding the hardware offering to include So like a security camera, window and door sensors, movement sensors. So right now, we've got just over 350,000 connected homes across Europe. We started in the Netherlands back in 2012. We're now live both with Eneco and through Interpolis. Back in 2016, we took the product to Belgium. We're working there with NG Electrabel, who are I think the largest electricity and gas company in Belgium. So a huge opportunity there. That's rolling out, and we're actually installing a lot more thermostats per week right now at NG. Back in 2017, so just over a year ago, we launched the product in Spain and really targeting a different kind of heating systems exist in Spain than within the Netherlands and Belgium. We're right now in a testing phase in Germany. We've got a couple of pilots underway, and that would be a huge new territory hopefully we can move to relatively soon. So to give a little bit of idea of the kind of products we offer, we've got in the center here, this is our smart thermostat, which you control by an app. You have very simple heating control. You're able to set very quickly a program, and here different modes: away, home, asleep, comfort. And at the same time also see real-time insight into your electricity consumption and gas consumption, along with customizable tiles. So here, for example, we're showing the time and the weather, and you can see you can customize this in a lot of different ways. So that's where we started. We've actually moved and expanded the product offering. I talked a little bit more already about the security offering we have with Interpolis. We're also moving in the other direction, so moving over to less hardware within the home. So this is an example of a smart meter dongle. So Dutch smart meters are being installed at a vast rate across the country. You can access data from these smart meters at, say for electricity, a 15-minute resolution without having any hardware in the home. But if you install something like a smart meter dongle, you can get access to the 1 second or 10-second higher resolution data. And on the far left, we have this option that just works without any hardware in the home, just reliant on that smart meter data. So really expanding the offering out a little bit. So that gives you a little bit of a flavour of our product offering. But today we want to talk a little bit more about applied machine learning. I want to share some of the experiences that we've had at Quby and really put that in the context of some of the other lectures that have been in this series. So real-world machine learning is quite different than in theory. This is a figure from Google. I hope some of you have seen it before. This is Google basically looking to see, of all of the code that's written for a machine learning project, how much of it is actually the machine learning code. It's this small part in the middle. You need so much stuff around that machine learning code to make the product and the services work. But you should make sure that this works really well, but you shouldn't just put all of your focus on in the middle there. So and this is something that we see really much at Quby. So if you look again, so the next level, the team that you would need to put together to deliver some kind of customer-facing product, delivered with having machine learning at the core, you're going to have some data scientists, data engineers, and machine learning engineers that help take a data science algorithm and make that work at scale. They're going to be building most of the things we saw on the previous slide. But on top of that, you need to add in front-end development, so building the app or the functionality on the Tone display. At the back-end development, making sure all of everything's connected together, that the right data is being shown in the right places. You've got the user experience, so you want to make sure that your users are using the product and the service in the way that they would naturally expect to. There's a lot of things you want to make sure that it's working in an optimal way. You don't want to be annoying customers that every time to get the information they want, they have to click 7 times when they could just click once, or you need to explain the information in the right way. Visual design is really important. You need to make this look appealing for people to want to use it. Product management coordinates all of this, looks to see what else is out there. Proposition marketing is looking to see, okay, you've got an idea, how do you sell that? How do you make people want to buy it? And then on top of that, sales teams, infrastructure teams as well. So as you sort of piece it together, you start with a machine learning algorithm is really at the core, but you've got all of this stuff that needs to build on top to actually create something usable. Give a little bit of a flavor for the kind of platform we're using at Quby. So we're using a technology called Apache Spark, which allows to do machine learning on distributed data. So that's something that's really core. That allows you essentially to run machine learning algorithms for hundreds of thousands of users at a time. So instead of, like, you might have played around a little bit training machine learning algorithms on your laptop and running generations there. If you're getting data that's all stored in different places, so we collect our data, typically and store that in AWS, that's Amazon Web Services, that's a cloud storage provider. You want to be able to interface and interact and use all of this data, both for the training of your models and also the generation of insight for end users. We use a platform called Databricks, which is an online analytics platform. And then we have a few things that tie it all together. So we use typically Scala or Python code for both production and R&D. And then we've got services like Apigee, which does API management, so managing the interfaces between the machine learning component and other components of the product. To give a little bit of a flavor for how do we actually go about creating services. So there's three core parts to it. Typically you start here. You're looking for desirability of the service. You're trying to find what does the end user want. So you're searching around and going, okay, a good example is, does the end user want to save money? Do they want to avoid wasting energy in their home? Then you start moving towards feasibility. So that's, okay, given the data and the technology we've got, what can we create to solve the problem of the end user? And then once you've got these two together, then you start iterating. You try to find technology that can help solve the user's problem and to reframe the way you're presenting that information to best suit the technology that you've got. That allows you to then explore the viability of the solution. That's really where you're looking to see, in simple terms, is someone willing to pay for what you've created? And you need all of these three together to actually make something work at scale. So the way that we've developed a lot of these services, we have a group of individuals we call the Tone Innovators. That's around about 1% of our user base. So in the Netherlands, about 3,000 to 4,000 users that have agreed to share their data with us for R&D purposes. In turn, they get to try out the services for free. The first ones to try it out. So that's a great way of doing these small iterations and learning actually what people want, what's possible to do with the data. I'm going to show a couple of examples today. One is something we call the waste checker. This was a product that we launched around about this time last year in the Netherlands. So the problem it's trying to solve is twofold. So on this axis you've got two things. From the utilities point of view, they're really wanting to maximize the level of engagement that they have with their customers. Increased engagement typically means lower churn, so less people moving away from the utility. But it doesn't need to just satisfy what the utility needs. What's in it for the end user, for the homeowner? There, you're looking to see sort of energy savings. That's something that, for me as a homeowner, that's something that really interests me. What we see is in the past, the traditional billing relationship of utilities. That's the once per year. At the end of the year, you get a bill, comes through. So you're not getting much interaction with the utility. And then you get it once per year, and it's typically quite a negative reaction because no one likes receiving a bill. Moving away from that, we're moving. So our Tone product has also offered the ability to see historical energy insight. So this being able to look back into yesterday, the last week, the last month, last year, how did you use energy? So that leaves a little bit more engagement, offers a little bit more potential for saving energy, around about 4 to 6% if you look at some of the studies. To get it to the next level of energy saving, then that's where you're bringing in real-time information. If you can see that if you're at home and you go, you switch on the microwave or the oven and you can see exactly how much energy you're using, that gives you even more direct feedback, and you can go, okay, I need to be perhaps a little bit careful how much I turn on the oven. Perhaps I'm going to have a different meal to cook tonight. Then to take it to the next level, what we've seen from academic studies is taking it really down to the appliance level offers people the opportunity to save even more energy. So this is, for example, instead of just showing you everything that's happening in your home, giving you specific advice what you can do with your washing machine. How much energy is the washing machine using? What can you do to reduce the energy consumption? Or just to understand how much you're using. So this is the product we launched. So this is within the app. It has a number of different use cases that we're giving insight to people on the appliance level. So we have right now 7 different use cases. So we typically take the approach of alerting people to inefficient devices and behaviors, and we typically give them a green or red rating. So here we're showing we can identify an inefficient washing machine, dryer, refrigerator and freezer, a dishwasher with the settings with the heating system, the standby usage or the always-on usage. So these are all of the devices that are constantly consuming energy within the home. And also an interesting one is looking into showering usage. Seeing you can have the option of having a more efficient shower head, which reduces the water flow, but leads to the same level of comfort showering. So there's a lot of new technologies out there that we can assist people with choosing. So to give a little bit of flavour more on the electricity use cases, a key technology behind the scenes there is what we call load disaggregation algorithms. So that's really taking the electricity data. So this is coming in typically 10-second resolution, and that includes all of the data, so all of the electricity consumption over the whole home. What we want to do is we want to split that into different appliance signals. So this is an example of what it looks like in a home. So this is one day. This is actually in my home. So you've got here, this is the electricity signal, and we're able to run algorithms and detect different appliances running. So we can see here we've got the washing machine running. It has so regardless of the kind of washing machine you have, the make or model, it is always likely to start with a period of heating up water. So it's a big peak in consumption. It turns around for a little bit and spins really fast at the end. I mean, I'm sure you're all familiar with how washing machines work, but you can see that within the data as well. Different appliances have different signatures. Here's an example of a dryer machine used and a dishwasher. We're able to pick out more smaller appliances. So just shown over the nighttime hours, we've got a refrigerator and a freezer, which typically tend to alternate between switching on for a bit, switching off, and switching on again. We're able to identify when there's sort of lighting or home entertainment being used. That's typically a level of consumption that's above the baseline and is relatively consistent for a period of time. I'd say our users try to make it complicated for us as well. This is another example from my home where we have a washing machine running, followed by a dryer, followed by a washing machine at the same time, followed by another dryer, washing machine, another dryer, another washing machine, a dishwasher, and finally another dryer to dry all of the clothes.
You have a large family.
Yeah, I've got 2 young kids. So we need to do a lot of washing. So it's relatively, if we look on the previous slide, like if you've got an appliance that's operating on its own, it's more simple to pick it out. It's when you've got all of these things happening at the same time, that's when it gets really complicated. But we've got algorithms that allow us to do that. But how do we go from there to actually give the advice to users within the app? So we start taking these disaggregation algorithms, we run them on every day of data. We then look back over a few weeks, a few months, and build up some kind of fingerprint of the appliance. So we could be looking, for example, at the washing machine. The majority of energy consumption is in that heating cycle at the beginning. So if you see for there's a very long period or very high power, then you can see that there's been more energy used. But that can be for a variety of reasons. It could be that someone has a very old washing machine, so a 15-year-old washing machine is just really inefficient at heating up water. Or it could be that someone's washing all of their clothes at 60 degrees. So that's why we were able to compare this with an industry energy consumption standards. So think, for example, a dishwasher or washing machine has an EU energy label. But, for example, heating systems and shower heads don't typically have the same level of detail. So that's why we also look at peer comparison. We've got data coming in for over 300,000 users across the Netherlands, so we've got a very good picture of what's happening across the board. And that's what we translated into a personalized insight for the end user. So in this case, we're giving notification that the dishwasher is being used inefficiently. That could be, as I suggested, a really, really old dishwasher that's really inefficient at heating up water, or it could be that someone's just using a high temperature program every day. If we put this all together, what kind of scale do we get to? So over these around about 300,000 users, we're detecting over 75,000 dishwasher cycles per day. If you took all of those dishwashers, ran them end to end, it would take 13 years for them to complete. So that's the amount of dishwasher cycles we're detecting. I never thought that I would know so much about dishwasher cycles. And importantly, 25% of all of these are being used inefficiently. So there's a real potential of saving energy across, if you scale this up to a whole country level. Before we dive into a little bit more details of some of the machine learning algorithms, I wanted to give you an opportunity, a little bit of a pop quiz. So based on our data today, what do you think would be the most popular day of the week to do the washing? Any guesses?
Sunday.
Saturday, Friday. It is Sunday. Saturday does come close, so we're talking. Yeah, 5 million to 4.9 million. If you dive into it in more detail, actually 10 o'clock Sunday morning, that's like prime time to switch on your washing machine. So this gives a little bit of an indication just for the scale of the data we've got. Since you did so well at that one, I've got another quiz for you. The most popular time to start the dishwasher, so both the day and the hour. Any guesses?
12 o'clock at night.
2 a.m.
2 a.m.
3 a.m.
I'm not hearing anything close. It's Monday at 6 o'clock in the evening. Actually, I looked into it in more detail. 6:39 is the peak time to start dishwashers. So I don't know. I got a lot of hypotheses about this. I think people have dinner 6 o'clock exactly. Maybe turn on the dishwasher just afterwards. Don't do so much. Exactly. Yeah, not doing the dishwasher on Sunday means more falls over to Monday, perhaps.
So this is when it runs, not when you set it to run at night.
That's true. Yeah, this is when it actually starts with the cycle.
Yeah.
Yeah.
So interesting to see here is that there is a peak like 6, 7 o'clock and later at night. So people set it on a program timer, which they don't do with the washing machines.
It's very true. Yeah, I think there's also the group of people that put on the dishwasher directly after eating, and then those are the ones that do it the last thing in the evening, either with a delayed timer or, like me, they just delay it until the end of the day.
But it's interesting because with washing machines you can do the same.
Exactly.
What your previous slide shows.
It shows you people really don't do that.
No.
So yeah, it's really interesting comparison.
Not according to my wife.
So what I wanted to go into a bit more detail today was three contrasting machine learning approaches. So actually for one of the use cases we have is identifying the type of dryer within the home. So it's a little bit simpler than some of the ones I was showing earlier. So we're really wanting to identify, does someone have a type of dryer that's inefficient? So for example, a more traditional style of dryer, or have they got more of an efficient dryer based on heat pump technology? So there's three different approaches that we've tried. There's the one event-based method, a random forest approach, and a deep learning approach. Overall, we're basically trying to go from the raw data, where we split up that data into chunks, because we don't want to be processing necessarily the whole day at a time. It's very unlikely that someone's going to be running a dryer for one cycle for the whole day. So we can look within maybe a 3-hour window, and we're very likely that the whole cycle is in there. Then we're looking to identify 2 different types of appliance. So we've got here, this is an example of the condenser dryer, so the more traditional dryer. It's a very nice rectangular block. It's an element switching on, it switches off for a little bit, switches on, switches off, and then finally everything switches off. The heat pump dryer is very different. It tends to be more of a smooth curve going as it slowly warms up, and then it has some spinning cycles at the end. And then once we've done that, we want to then present it in the NGs, in the application. So the first of the 3 approaches is the event-based method. So this is in disaggregation algorithms and sort of from a signal processing approach. It's quite a traditional approach. It was first talked about in 1992 by G.W. Hart, where you're basically looking for on events, so something turning on, and off events, and you're trying to match the 2. So in this example, we've got an oven turning on, and then a little bit later the oven turns off. And if you can match something that's around about the same size, you think, okay, in the middle, it's likely to be an oven. You can do the same thing for a refrigerator that's cycling more rapidly. The second approach is more a random forest approach. So this is basically where you're taking some kind of decision tree. So you have some kind of input vector. You're wanting to do a classification, and basically at the end come up with a probability of which class you're sitting in. The random forest, I hope you've seen a little bit in some of the previous lectures of this series, is where you take one of these decision trees and then create a whole load more, put them all together and see what you're getting on balance. That's shown to have a lot higher predictive power. What you want to do with a random forest approach is you want to specify which features you think are important. So based on expert knowledge, you can identify things like, say, the mean and standard deviation of the derivative of the power signal. So that's something that, it's going a little bit back to the event-based approach. If you're looking for something switching on and off, then you can imagine that the derivative is going to jump up at times when something's switching on or off. And then there's a lot of other features that you can propose, and you can train a random forest. You can see actually which of these features has the most predictive power, and then build a model from there. Finally, there's a deep learning approach. So whereas a simple neural network typically just has one hidden layer in the middle, a deep learning neural network has multiple layers in the middle. Give a little bit of a flavour for the kind of deep learning approach we've taken. If you want to know more, we've actually written and submitted this as a conference proceedings paper. My colleague presented it in Washington, DC a few months back. So I can share you the link there if you want to know all of the details. Feel free to look there. Essentially what we're doing is we're starting with electricity data, probably within a 1-hour window. Then we're running some kind of convolutional layer. That's where you're passing a number of filters across the data to try to pick out different patterns. It's a very similar approach as what you'd do if you were trying to process some kind of image data. You'd be looking for run different filters. Some of them are going to be looking for edges, some of them are going to be looking for gradients, some of them are going to be looking for even more complicated patterns. Then we move towards 2 layers that are both based on an LSTM, so that's a long short-term memory component, and it's bidirectional, so you're able to learn in both directions. So all of this part, the first 3 steps, are really where you're learning the features. You're trying to understand, okay, what's in this data, what am I seeing? And then you move on to the classification step, and here we've taken a couple of different layers. These are typical fully connected layers, so there's all of the neurons are connected to all of the other ones. And then finally we take it to just a simple layer with 3 outputs. So if it's 0, we say, okay, within this 1-hour window, we don't think there's any dryer. One, we think it's a condenser dryer, and two, we think it's a heat pump dryer. We can have a relative probability across all of these categories. So, which method is the best? If you were to look at it maybe from just the textbook approach, you'd go, okay, well, the event-based approach only really works for one dryer type. It can't pick up the heat pump dryer because, as we've seen before, you don't really have that on and off step. But the precision is adequate, recall is quite high. The random forest approach it allows you to detect two dryer types. Precision's really good, recall kind of a bit better. Deep learning approach puts precision up really high, detects both dryer types. Recall jumps up a little bit more.
Yeah, silly question, but what's recall?
Okay, good question. Precision is essentially if I tell you you have a heat pump dryer, how likely am I to be correct?
Yeah.
Recall is how many of all of the heat pump dryers out there do I actually detect?
Yeah, so it relates to false positive, false negative.
Exactly. Yeah, it's a ratio between all of those. Then the next thing is in a sort of industrial concept, you're looking in terms of extra things that are important. So adaptability. This model works really well in the Netherlands with Dutch meter signals and Dutch dryers. But how easy would it be to train it on some new data? Event-based, you'd have to really start from scratch probably and test it all out. The other ones, it's a data-driven approach, so you're better suited. And then really importantly, daily calculation time. So you need to run this every day. So that's not the training of the model. That's actually just the physical, like you're basically calculating just a lot of linear algebra every day. Event-based, really simple. Random forest jumps up a bit. Deep learning, whoa. And in an industrial context, that means money because you're paying for the compute time for all of these. So, given all of that, which approach is the best? So there isn't a simple answer. But where we started with Quby, we started with the event-based approach. We actually got a lot of feedback from our end users that for those ones that had a heat pump dryer, we weren't able to tell them that they had an efficient dryer. We were just telling people that had an inefficient one. So we were getting a lot of feedback saying, hey, I want to get a green tick in my app. So then we looked at a couple of different approaches. We've actually right now have the deep learning approach running in a production setting. The random forest approach is also something that we can adopt as well.
And why is the hidden Markov model not included? Because hidden Markov model to me sounds like a very natural fit, right, for these linear time series data.
It is a natural fit. There are some.
It's cheap to at least to apply, right?
It is cheap to apply, and we did actually try that as well. We found actually that I can't remember if it was the precision or recall, but just we weren't able to get it up to the level of a more complex model. So, it's really good to start from absolutely the simplest and try to find out the simplest model that fits the requirements. So let's move on to the second use case. So this is detecting anomalies in heating systems. So what we have in our existing boiler monitoring service is we're essentially able to give people alerts when they have maintenance needed, or certain types of boiler that operate using what's called an open therm protocol are able to send additional information about the error status. So that's where, for certain types of boiler, we can send error messages. But what we wanted to do is to develop something for all types of boiler, because not all boilers are open therm. In the Netherlands, it's roughly a 50-50 split. If you move to other countries, some countries haven't even heard of open therm. And not all problems with the heating are caused by a failure with the boiler. It could be, for example, that it's the end of summer and all of the valves on all of the radiators are closed and someone's at home going, well, I've turned on the heating, where's my home not heating up? It could be something that someone's decided to open all of the windows, all of the heat's going out the windows. So we've developed an approach that uses streaming technology that covers all boiler types. Quickly running through how it works, we're essentially monitoring both the boiler status, whether the boiler's being requested to switch on or not, and the temperature, typically in the living room, and trying to identify mismatches. So here we're seeing the boiler is asked to be on at full power, but the temperature in the living room is dropping. That's a sign, okay, something's up. What we see here is essentially this is one home, and its normally behavior would be in a typical range. If we move outside of that range, how do we pick things up? You can use a variety of approaches there. A very simple approach is just to have some kind of rule-based system that if you move into this zone, then you're going to say something, an anomaly is happening. Then we want to take into account the severity, user preferences before deciding whether to give an alert or not. So this is another problem we're focusing on. Right now, doesn't have nearly as much complex machine learning behind the scenes as with the previous example I showed. I think it's good just to put it in context of some of the problems we're facing. Finally, just wanted to wrap up with, we work with a lot of external parties, universities and research institutes, both in the Netherlands and abroad. And yeah, it's very, we've got a lot of benefit out of sharing the knowledge that we've derived from working on this industrial problem. Thanks very much.
Thank you very much. Very interesting. I mean, also, if you have such a machine at home, you can some more background now. So, any questions from people? So, how do you, with the deep learning network, how did you come to this eventual configuration? Because it seemed pretty complicated compared to the earlier ones.
It is pretty complicated.
So
there has been academic research in this area for a while. There's been because people have kind of seen the potential that a deep learning approach has for this kind of problem. So it was definitely informed by previous studies that have gone on, plus a lot of trial and error, essentially. That's one of the difficulties of having such a complicated approach is there's many different options for even the number of layers you want to have, the size, the different types of layer. It's very difficult to come up with something that's optimal, but as long as it's good enough for the problem at hand, then it can work pretty well.
Okay. Any other questions came up?
Yeah, so maybe from a privacy perspective, right? So you're collecting a lot of data from people. So do the users have a right to get their data deleted? Can I download my own data? Stuff like that?
Yes, and yes. So you can actually download all of your data from within the thermostat itself. So there's an option on the display. Mm-hmm. And we also we're very sensitive about how we collect data because this is incredibly personal information. Because you can see how people are using appliances within their homes.
I could infer that you have a family.
Exactly. So that's why we're very careful about how we store and use the data, and it's actually only when people are starting to use our services that then we actually combine it together. So if you were to sign up for the service, before you did that, I would know that there was a house with some electricity going on, but I wouldn't be able to match it up to your particular home. So that's why we need to be really careful, particularly with different European privacy regulations that came out this year.
That's going to be my second question. So how much did you need to change about your business model with the GDPR that was installed earlier this year?
I think the biggest thing with the GDPR is before GDPR it was a little bit unclear whether the data we were collecting was, if we sort of pseudo-anonymize it, so we create all of the data and give it some kind of random identifier, whether that means that it's anonymized enough that it shouldn't be treated as personal information or personal data. Actually, with the GDPR, that's actually helped to clarify things. In simple terms, all of the data we're collecting is personal data. So we need to be at the strictest level of dealing with that for everything. So in that sense, it actually made things a little bit more straightforward for us, because prior to that we were having to make an educated choice of how much anonymization we were going to apply. We still apply that approach, but that's more for the benefit internally, that it helps the systems to work really well.
And just out of curiosity, how much training data do you need to recognize, say, a dishwasher?
Good question, yeah. So we actually, to get sort of a source of the labeled data, the truth data, we installed smart plugs in around about 150 homes, and I think we collected data for over a year in the end. So that then you can basically, you've got a label, you know exactly when the dishwasher is being turned on, and then you can train from there.
So it's probably 20,000 dishwasher cycles.
Something like that. I think you could do it with less, but we were lucky enough to have access to that. Yes.
Is your company also having something like, or working on something like an unsupervised learning algorithm that kind of tries to perfectly heat your home? So, yeah.
So we actually have, so as part of our heating algorithm, we do actually take into account, it's a learning algorithm, so it will learn, for example, the different characteristics of your home, so to make sure that if you want your home to be at 20 degrees at 7 o'clock in the morning, that it knows exactly when to start heating up. Interesting on top of that, a big waste of energy is people heating their homes when they're not at home. So to be able to offer services that more optimally heat homes is something we're really looking into. Right now, we particularly see in the Dutch market, most people want to be sort of in control of their heating. So sort of a halfway measure there is really to give like a suggested thermostat program. So we would be able to identify perhaps from your, even the washing machine data when you're more likely to be at home or not, and we can say, okay, does this fit with what you think your pattern is of being home or not? And then suggest a thermostat program. To take it to the next level and making it completely fully automated, we're not seeing the customer demand for that right now. It's certainly something that me and my team are investigating, what the technical limitations are and actually how good we can make it.
Could you say something about the effect of the wasting signals? Do people spare energy?
Yeah. So we're actually conducting a study right now with ECM, we've been looking over an extended period of time to see how people save energy. So the initial results show that there's a definite decrease as soon as people start using the app.
Okay.
But as with all of these things, it's followed by some kind of rebound effect.
Okay.
And it's because a lot of it, like if you save energy in one part of your home, then you can quite easily spend it in somewhere else, go out and buy a new gadget or upgrade the TV that you had to a nice new one.
The weight loss effect.
Yeah.
It's really similar to that actually. So there's definitely an effect of the app, but the long-term effects, we need longer to study it essentially. Yes.
So you are talking a lot about making improvements to the system, but I would believe that the data is also very interesting just in an academic perspective, as in how do people use their energy at home.
Yeah.
Is that something you also want to do, or do you share your data with?
Yeah, we've actually been working with TU Delft for the last year and a half, enabling them to do some research studies on that, and also been in, some of that is being used by the Dutch government as well, or at least has the potential to be used by the Dutch government to understand how are we using energy in homes across the country, because it really gives a sort of a magnifying glass that enables you to see an extra level of detail that was not available previously.
Can you give me a feeling for the amount of compute that you guys need to do in the cloud to kind of service all these homes?
What unit would you like?
Well, cost is one thing, but I mean, you must have a cloud provider that. So, do you know per home how much you need to calculate?
It's hard to say per home because we have a lot of things that are running at once. We typically there's two different kinds of compute that we're doing. One is, I take you back through to this one. So the first thing is identifying when different appliances are running. That's typically multiple models that don't get trained very often. And then you've got this step where we're actually, across all of the use cases, we're calculating, I think, almost every day 1 million smaller classification models. Overall, we have quite a large cluster we're running on, I think around about 150 CPUs.
Yeah, and that's in-house?
No, that's actually through AWS.
Okay.
So we don't do any of this in-house. It doesn't work economically to do that these days. And that is running for typically less than a couple of hours to process a day's worth of data for a few 100,000 users.
Yeah.
So that's a trade-off. That's sort of the level we're dealing with. If you look at the level of data that we've collected from all of these homes, we've been collecting it for almost a couple of years. We're getting around about 100 megabytes of data per user per month. So in total, that's around about 1.5 petabytes of data in total right now. It's a little bit of a...
It would be worth calculating the amount of energy you save. To store the data, to compute the data.
I have made those calculations.
Okay, it's still positive.
It's still positive there.
Okay, I think we'll stop otherwise, we can talk to them later.
Yeah.
So, which one is it, white or red? Right, okay. So thank you again for the nice talk, and let's speak to you.